Now that we understand there is an integral relationship between the loads, the internal shear force, and the internal moment, we can use this to quickly generate shear and moment diagrams that allow us to know what the internal forces are all the way across the beam. So let's start out simply with the cantilever beam and analyze the reaction forces and draw the shear and moment diagram. Now, it's a cantilever beam. It has a fixed support. The fixed support, we'll call this support A, gives us a reaction in the Y, RAY, reaction in the X, RAX, and a moment A. If I go through and find the reaction forces, I can sum the forces in the X. They have to equal 0. 0 will equal RAX. If I sum the forces in the Y, they have to equal 0. 0 will equal RAY minus P. RAY will equal P. And if I sum the moments around A, that's equal 0. 0 will equal minus MA plus P times L. MA will equal PL. So I can take all those things and put them over onto my diagram. Where we have RAY acting up, MA acting counterclockwise, and RAX equals 0, so it doesn't really act in way. I'm going to draw some lines straight down to help me draw my shear and moment diagram. Now, as we understand, we know that shear is equal to the integral of minus the load function, and the moment is equal to the integral of the shear. On this cantilever beam, we don't have a loading function. We have an impulse load of P on the end. So over the entire length of the beam, except between the supports, we know that the loading function W is 0. If we go on to integrate 0, and I'm not doing the formal integral of 0 is 0. But if I think of the integral as more of the antiderivative, I know that we'll say that the shear is equal to some constant. The way we evaluate this constant is with a boundary condition. Our boundary conditions are applied by our supports. So at 0, we know that the shear force has to be equal to the reaction RAY, which equals P. So we can say B of 0 has to equal P, so that P equals C. If we know P equals C, our shear force has to equal P. So if we go and draw our shear diagram, I'll draw in green, it is constant over the whole length of the beam because there's no forces anywhere else on the beam to cause it to change, except for at the beginning, where it will jump from 0 to P, and at the end, where it will jump from P back down to 0. Your shear and moment diagram must always begin and end at 0 because they're in equilibrium. When you have point reactions and loads, what those point reactions and loads do is they cause your shear diagram to jump. Loads cause your shear diagram to move, Shear will cause your moment diagram to move. If we go and say moment is the integral of shear, we know that moment is the integral of P. If we integrate P, we find that moment equals Px plus C, another constant. In this case, we know the moment at 0 has to be minus PL. So we can say m of 0 equals minus PL. We know that minus PL has to be equal to P times 0 plus C. C equals minus PL. So our moment equation is, I'll just write it in because I'm running out of space, Px minus PL. What that will be is at 0, we'll have minus PL, and we'll go from 0 to minus PL, which constitutes a jump. And that jump is caused by this point moment going negative. So we go from 0 to minus PL. Px minus PL is the equation of a line. And if we put L in for x, we'll get PL minus PL at 0. So it's a line that goes from minus PL to 0. And notice, given our equation and our point moment, everything begins and ends at 0. And our integral relationship holds. We have 0. If we integrate 0, we get a constant, and our constant is shear. If we integrate a constant, we get a line. So our moment is linear. Here we have the same cantilever beam with a linearly distributed load of W. In order for us to find the reaction forces, we need to find the resultant force. For a linearly distributed load, the constant force is just W times L, which gives us a force. The units of W are force per length. If we multiply it by the length, we end up with a force equal to WL. Given our constant sign convention, we have a fixed support, which again has a y component, an x component, and a moment. If we sum forces in the x, they have to equal 0. RAX will equal 0. If we sum forces in the y, they equal 0. So we'll have 0 equals RAY minus WL. RAY will equal WL. And if I sum the moments around A, they have to equal 0. 0 is going to equal minus MA first, plus WL times L, which is WL squared. MA will equal WL squared. So RAY is WL. M is equal to WL squared, but it's not actually WL squared. I'm sorry. It will be WL, which is applied at L over 2. So this should be WL times L divided by 2. So this will be WL squared over 2. Now, an important point to make about the resultant before I do any shear and moment diagrams is that the resultant force is only used for the reactions it does not come up anywhere in the shear and moment diagrams. So I'll draw some more lines to help us draw shear and moment diagrams. again, we know that shear is equal to the integral of minus w. In this case, our loading function is a constant, w. So we are going to integrate that actual w and find out that shear is equal to minus wx plus a constant. The shear at 0 is equal to WL. So we can say V of 0 equals WL. If I plug in 0 for x, we find that WL equals C. So shear is equal to minus WX plus WL. So at x equals 0, the shear is a positive WL. If I plug in L for x, I find that the shear is 0. This is a line that goes from WL, to a better line than that, to 0. And the equation is minus Wx plus WL. So in this case, we had a constant load. The integral of a constant is a line, so we have linear shear. Since the integration holds, we're going to end up with a parabolic moment. So moment is the integral of shear, which is minus Wx plus WL. If we integrate it, we find that the moment is equal to minus Wx squared over 2 plus WLx plus C. We know the moment at 0 equals minus WL squared over 2. If we plug in 0 for x, we find that the moment equals, and since I'm short on space again, I'll just erase the C here and replace it with minus WL squared over 2. This is our moment diagram. If we plug in 0 for the x, we'll find that it equals minus WL squared over 2. And it will be parabolic, concave down, going up to 0. If we plug in L, we'll get minus WL squared over 2 plus WL squared. The minus WL squared over 2 will become minus WL squared, and this will become 0. So we'll have a parabolic curve connecting from here to here with the equation of minus Wx squared over 2 plus WLx minus WL squared. Okay. But again, shear is the integral of the negative load function. Moment is the integral of shear. If the load function is constant, we end up with linear shear. If the shear is linear, we end up with a parabolic moment. Now, here is one final problem where now we have a uniform load of 100 pounds per inch and a point load of 1,000. Now, this may look familiar because all it is a combination of our last two problems. Now, in all of statics, all the forces and the things we do, you can use the theory of superposition. The theory of superposition allows you to do two things differently and add them back together. We could go through and find the reaction forces for both the 100-pound per inch force and the 1,000-pound force and add them together and get the total reaction forces. And then by adding together the reaction forces from each separate piece. Now, in the way I've done my example, we did the examples completely without numbers, which means that we can go about and use them for solving more complex problems. So I'm going to go take a picture of both of these. And use them to solve different problems. Because what we have here is just a superposition of a beam with a uniform load on it with a beam with a point load on it. And here I've moved over both their shear and moment diagrams. The only thing I didn't do is I cut out the equation. Grab that. Now, to solve for our current problem, all we need to do is add together the things that we've done before. That all the way over there. This. And we can just go about solving the problem we have at hand. So first off, superposition works for our reaction forces. So for the uniform load, our RAY is WL, and for our point load, it's P. So in this case, RAY will equal 100 times the length of 60, so 6,000, plus our point load of P of 1,000. Our RAY will equal 6,000 pounds. RAX is 0. The moment from the point load is PL. The moment from the uniform load is WL squared over 2. I can do PL, which will be 1,000 times 60, so 60,000. That's going to be plus 100 times L squared, which is 60 squared, divided by 2. I'm not going to be able to do that in my head, so I'm going to grab my calculator. Say 100 times 60 squared divided by 2 is 180,000. So we'll have 60,000 plus 180,000 is equal to 240,000. And since it's a moment, it has units of pound inches. But we can get our reactions by superimposing the two reaction forces. We can get our shear and moment diagram equations by superimposing our shear and moment equations from our previous problems. So our previous shear diagram for a point load is a constant P. the shear diagram for the uniform load is linear, so we can add these two things together. Our equation is going to be a linear portion on top of a constant portion. It will go on and look something like this. Where the uniform load ends at 0, the point load ends at P. The end of this diagram is going to be the value of the point load, which is 1,000. This point up here is going to be the 1,000 plus W times L, which is 6,000. This will be 7,000. The slope of this line will be the equation for this line will be 7,000 minus the W is the applied load, which is 100 times X. The equation for this is 7,000 minus 100X. Okay? Now, if we want to get the moment diagram, it's going to be some weird line, combination of a line and parabola, and we could go in and plug the numbers into our moment equation for each of the things and add them together. I think at this point, though, it might be easier just to go through and do the integration, because it's easier to integrate 7,000 minus 100x than it is to add all those things together. At least it is in my mind. So let me clean. And we can say that the shear is equal to 7,000 minus 100x. Moment equals the integral of 7,000 minus 100x. Moment will equal 7,000x minus 100x squared over 2 plus a constant. We know the moment at 0 is equal to 240,000. So we can say 240,000 is equal to 7,000 times 0 minus 100 times 0 squared over 2 minus plus C. We know that C equals minus 240,000. So we can go back and say that our moment equation is equal to minus 200,000. And I think doing that integration from the combined shear diagram is a little bit easier than just doing the combination. But I encourage you to go back, plug the numbers into the two different moment equations and add them together, and it should come out to equal the moment equation we found through integration. Superposition can help you do more complex things. It lets you break down more complex problems into simpler problems and then just add the results together.